Now part 2 of the video is going to start with a review. One of the most basic formulas we know and you guys have been working with since probably 6th or 7th grade is the Pythagorean theorem. Main thing is this is only good for right triangles, and it's a way to find and relate the lengths to each other. So the right angle is key because that always points at the hypotenuse, and the other two are called legs in a right triangle. And so the hypotenuse is always first, and we say c squared is equal to a squared plus b squared. Basically, the hypotenuse squared is equal to leg squared plus leg squared. So if you can always identify your hypotenuse, you can get your equation set up properly. As long as you know 2 of the 3 sides, you can set up this equation and solve. And now you see with the squaring in this equation why the radical practice, taking the square root, is going to be necessary. So let's look at some examples. If I have a right triangle with a leg of 6, a hypotenuse of 10, and an unknown leg, I can say 10 squared is equal to 6 squared plus b squared. So 100 is equal to 36 plus b squared. Subtract 36 from both sides. 64 is equal to b squared. We undo squaring with the square root. Now we know that typically when we take the square root, we get plus or minus 8. But in the context of a real problem like this, the negative is an extraneous solution, and so b is just 8. And that's going to be the case for most of these problems because we are using the variables as lengths. We are not going to need that negative value. In this case, you know the 2 legs. You're missing the hypotenuse. You can give the hypotenuse whatever variable you want. Typically in triangles, remember way back to quarter 1, the vertice has a capital B, its side opposite has the lowercase of the same letter. So this side opposite would be called A, and this side opposite would be C. The hypotenuse does not have to be C. So this is our hypotenuse, not because of a letter, but because of its position to that right angle. So that's why I always draw that arrow in. So here I have b squared is equal to 5 squared plus 12 squared. So b squared is equal to 25 plus 144. If you don't know your perfect squares up through maybe 15, you might want to practice. It makes the problems go a little quicker. So b squared is equal to 169. Square root both sides, b is 13. Now, continuing on with some examples, notice these directions of exact. So that's where you're going to have to leave a radical in if you don't end up with a perfect square. Now, I have an isosceles triangle here because of those marks. So this side is also 5. Initially, that doesn't seem to fit our Pythagorean theorem, but I do have a right angle right there. And if I remember back to the first unit, if I have a perpendicular and these legs are equal, that means that perpendicular is the perpendicular bisector, which makes those pieces equal, which means this piece right here is 4. So now, on this half of the triangle, I can go ahead and solve for this missing height. Here's my right angle. So 5 is my hypotenuse. So I have 5 squared is equal to a squared plus 4 squared. 25 is equal to a squared plus 16. 9 is equal to a squared. A is 3. So you are perhaps going to have to draw back on some of that old knowledge about perpendicular bisectors or some of those other pieces. In this case, here's my right angle. 12 is my hypotenuse. Remember, your hypotenuse is always your longest side. If you've done your work and you end up with a hypotenuse that isn't your longest side, you need to go back and check your work. So in this case, I have 12 squared is equal to x squared plus 8 squared. 144 is equal to x squared plus 64. When I subtract both sides, I end up with 80 is equal to x squared. Now I'm going to take the square root of both sides, and x is the square root of 80. Now, do I have all of the perfect squares out of that? Well, I know it's 4 times 20. There's a perfect square. I know 20 is 4, perfect square, times 5, prime number. So I really have 4 squared times 5 is 80. So x is the square root of 4 squared. 4 left over is 5. That is the exact answer that we are expecting. So we have one more example on this page, and it has something crazy like an expression. So we still set everything up the same. Here is my hypotenuse. X squared is equal to 4 squared plus, this is a single number, so get those parentheses around, the quantity squared. Now that means here I need to FOIL. This is not, big algebra error right now, it is not x squared minus 4. That is a big boo-boo. You don't want to do that. This literally, remember, is x minus 2 times x minus 2, because that's what squared means. Okay, so you don't want to do that. So I have x squared is equal to 16 plus first two terms, outside terms, inside terms, last terms. See how different that is from that? Combine like terms. X squared is equal to x squared minus 4x plus 20. Remember from our algebra unit, if you have an x squared and an x, you need to get everything on the same side. And when I go to start doing that, I see that my x squared and my x are going to cancel. So I'm going to end up with 0 is equal to negative 4x plus 20. That's very nice. Now I can get my x by itself. I'm going to go ahead and add 4x to both sides. Divide by 4, and x ends up being 5. So don't get scared if you have an x squared, because had that stayed in the problem, then I just would have gone ahead and factored the way that we had practiced and reviewed in our previous unit. So word problems are also quite common in trig, and the most important thing in a word problem is to draw a picture. They are key. So the foot of a ladder is placed 6 feet from a wall. If the top of the ladder rests 8 feet up on the wall, how long is the ladder? So I draw my building. Here's my ground. We assume our buildings are straight up and down, and here's my ladder. If my building is straight up and down, that means I have a right angle, and we can clearly see this right triangle has formed. So now I fill in what I know. The foot of the ladder is placed 6 feet from the wall. That means that this is 6, the foot of the ladder from the wall. If the top of the ladder is 8 feet up the wall, so the top of the ladder is 8 feet up the wall, how long is the ladder? That's the one we want to know. That happens to be our hypotenuse, so L squared is 6 squared plus 8 squared. L squared is 36 plus 64. Now we know L better be bigger than 8 or 6 because it is the hypotenuse. And so L squared is 100, so L is 10 feet. And that makes perfect sense in the context of our problem. Now this next one is fun because you have to think about what the picture is going to look like. In the Old West, settlers often fashioned tents out of a single piece of cloth thrown over tent poles, then secured to the ground with stakes, forming an isosceles triangle. How long would the cloth have to be so that the opening of the tent was 4 meters high and 3 meters wide? So let's think about this. So here's my ground, here's my tent pole, and I have a single piece of cloth that's thrown over. Now, I want 4 meters high, and I want the opening to be 3 meters wide. So how long does the cloth have to be? So ultimately, I need to know that entire length there. But if I can find this length, I can just multiply it by 2 because it's isosceles. So I'm going to go ahead and I'm going to look at this triangle right there. And if you remember what we said in the previous example about perpendicular bisectors, if this is 3, that makes this 1.5. This is our hypotenuse. And so I can set up that h squared is equal to 4 squared plus 1.5 squared. Since we are talking about a length, decimals are an appropriate answer. So when we work this out, we have h squared is equal to 16 plus 2.25. H squared is equal to 18.25. And when you go to your calculator and take the square root, you end up with h being 4.3. But remember, I want the total length of the cloth. And so 4.3 times 2, my cloth needs to be 8.6 meters. I'm always careful to answer the question. Now, determining if something is a right triangle or not is simply a matter of, is the Pythagorean theorem true? If you set that equation up and it's true, you have a right triangle. If you set it up and it's false, it's not a right triangle. The trick is knowing the longest side. So in this case, clearly 5 is the longest side. So is 5 squared, is that equal to 3 squared plus 4 squared? 25, is that equal to 9 plus 16? 25 equals 25. So this means yes, this is a right triangle because it satisfies the Pythagorean theorem. When I look at this next example, if you think about it, the square root of 8 is our longest side. So this is our potential hypotenuse. So is the square root of 8, is that equal to the square root of 5 squared plus the square root of 3 squared? Well, the square root of something squared cancels. So is 8 equal to 5 plus 3? And it is, therefore, it is a right triangle. If I look at this example, 13 is my likely hypotenuse. So is 13 equal to 11 squared plus 5 squared? Is 169 equal to 121 plus 25? Well, 169 is not the same as 146. Therefore, this is not a right triangle. So it's kind of like applying the converse of the Pythagorean theorem. One of the little tricks that you may see and notice is there are patterns. They're called Pythagorean triples. So 3 sets of side lengths that always form right triangles, and they repeat it themselves in multiples. So 3, 4, and 5 are Pythagorean triples, as is every multiple of 3, 4, 5. So if I multiply them all by 2, 6, 8, 10 is always a right triangle. If I multiply them all by 3, 9, 12, 15, always a right triangle. So this is kind of a shortcut to having to do the Pythagorean theorem all the time. Another common triple is 5, 12, and 13, and all of its multiples, like 10, 24, 26. So as you start to see those patterns, it can save you a little bit of calculations. So try the next couple of homework check problems, and good luck on your homework.